Alright. So guys, to start off with, okay, we are going to start with the third law of thermodynamics today, and just to kind of review, could you please give me a one-word definition, your choice of word, of what the word entropy means? What would you say, Chris? Randomness. Give me another one. Disorder. Another one. Chaos. Messiness. Okay? Can you tell me what's another name for this temperature? Xander.
Absolute zero.
Absolute zero. Okay? Ladies and gentlemen, there are labs around the world who are dedicated to doing nothing more than trying to achieve absolute zero. It has not yet been achieved. Okay? They have gotten, scientists have gotten very, very, very close. I don't have a number to give you, okay, but I want to say like within thousandths of a degree. Okay? What's the importance? Well, the theory is, and again it's a theory because it has not been achieved, the theory is that at absolute zero, all motion stops. Okay? As you hopefully remember from Chem 1, all atoms, molecules, even if they're in solid form, even if it's very cold outside, have motion. Okay? And the theory is, not only would all motion stop, but all atoms, molecules, and ions in particular would line up in a perfectly aligned way. Okay? If the word entropy means disorder, okay, would you look at this picture on the left and say that this one has perfect order? I would. Okay? So the theory is that if you can get down to absolute zero, entropy also becomes zero. There is no disorder anymore. It's a theory because it hasn't been achieved. Okay? But if this is, you know, this is disorder, this is entropy, this is perfection. Okay? And again, the theory is that if we're at any other temperature, which we always are because, you know, we're not going to be at absolute zero, entropy values must be higher than zero. Now, ladies and gentlemen, go to the very back of your textbook, to that appendix, page A20, please. Alright, now we have used this chart before. We used it back in chapter 6. However, this chart back in chapter 6, we were only concerned with one of the three columns. Which one did we look at? Delta H. Okay, what is delta H? Change in enthalpy, heat energy. Okay. Well, folks, we are now familiar with the other two columns. The middle column is delta G. Do you remember from last class what that G stands for? Gibbs free energy. Okay. And the final column has entropy values. And just as an example of something, I want you to find in that chart solid iron, and please tell me its entropy value.
27.
27 what?
Kelvin.
Okay, per Kelvin mole. Okay. Find this molecule and tell me its value. It's written exactly like this. This is representing a double bond.
274 joules per kilo per Kelvin.
Okay. Now I want you to look at those numbers. They both have some amount of entropy. And by the way, don't ask me how you put a number on how disordered something is. I don't know, okay? There are people smarter than me that have figured that out. All right? But what I care more about is look at these two numbers in comparison to each other. Do you think this second molecule here looks more complex than this one?
Yes.
Yeah, it is more complex. And thus, it will have a higher value of entropy. Okay, that should make sense to you. The simpler elements, because this is just a pure element, simple elements have smaller values for entropy. Yep.
So,
Now, if you would also take out your equation sheet and be on the back where that thermochemistry section is. Does this look familiar to you? It should. We've seen this before, and when I pulled it up the first time in chapter 6, you all went, "Ah, it looks horrible." And then we realized that it turned out to be actually something very simple. Products minus reactants using the values from the back of the book. The only difference is it's not delta H anymore, like we did in chapter 6. Now it's values of entropy. You can do the same process. Okay? Alright, and let's review a little further here from last class. Okay, you just told me that delta G stands for Gibbs free energy. Do you recall from last class, what is the reason why we would ever want to calculate a value for delta G? Meg, what's the reason? Very good. To see whether a reaction is thermodynamically favored or not. Do you remember what kind of numbers indicate that? If delta G is what, Austin? Okay? Any number below 0. Any number that is negative means what? That it's favored. It's spontaneous. Any delta G value that comes out to be positive means not thermodynamically favored. Okay? And look, you can do the exact same thing for delta H, delta S, and delta G. Right? And we have another equation that we looked at last class that also involves delta G. And guys, just take a glancing look at your equation sheet in this thermochemistry section. All of this good stuff is given to you. You don't have to memorize anything. It's all here. And tell me this. Okay, let's just recap here. If the purpose of delta G is to decide whether a reaction is favored or not, and you now have two options for how to solve for delta G, how do you know which equation to use? What do you think?
based on the information you're given.
Exactly. It depends on what information you're given. If I'm given an enthalpy and entropy values, then I'll use this one. If I'm given values from the back of the book, then I'll use this first one. Depends on what you're given. Okay. So, I'm going to have you do this problem, and I want you to remember what I told you when we first looked at this chart in the appendix of your textbook. That when we take our test, am I going to let you get up in the middle of the test and get a textbook and open it up? No. How am I going to handle the situation that you need values out of here? I'm going to give them to you. Just like this. Okay? Any value you need, no, I'm not going to have you get a textbook. I'm going to give it to you. Okay? So given this reaction, and the data given to you in this table, I want you to solve this problem. Go. Were you careful with your units?
Oh, joules and clips.
I'm not doing that just to be cruel. That's how the information is presented in the book. So tell me, based upon this final answer, delta G is a negative number. Is this a favored reaction?
Yes.
Yes, it is. Okay. Thermodynamically favored. All right. This will be a little bit of review from Chapter 6. Do you recall from Chapter 6 what a Hess's law problem looked like? Remember those? These were the ones where I gave you what I called mini reactions, and you had to move them around. Sometimes you had to flip them or multiply them and add them together so that you end up with an overall reaction that you're supposed to. You remember those? Okay. Well, in Chapter 6, we were doing those with delta H values, enthalpies. But you can do the exact same process with Gibbs free energy values. Okay, so let's just kind of review how we did those. These are my two mini reactions. This is the overall reaction. Okay, carbon diamond, here it is. Is it on the correct side?
Yes.
Does it have the correct coefficient?
Yes.
Okay, so this one's good to go. Carbon graphite. Is it on the correct side? No? Does it have the correct coefficient?
Yes.
Okay, so how do I fix this problem?
Switch the colors.
Okay, flip it. And when you flip a reaction,
Change the sign.
you change the sign. Okay, I'm going to cross this one out because this is gone. If I add these together, do you see anything I can cancel out?
CO2.
Okay, CO2 and the O2. And I'm left with what I want. You don't even need a calculator. What's the delta G for this reaction?
-3.
-3 kilojoules. Okay. Is this favorable? Yeah, Xander says kinda. Well, you're right. It is favorable, but only kind of. Look at what's happening here. Diamonds are turning into what's in your pencils. Spontaneously. That is a spontaneous process, people. Now, here's the reason I chose this example specifically. Just because a reaction is favored, is spontaneous, happens without your help, doesn't mean that it happens quickly. Okay? Alright? So do I need to be concerned that the diamond in my wedding ring is just all of a sudden one day going to turn into a chunk of graphite? I mean, maybe a million or billion years from now? Sure. I'll be dead by then, so will you. Okay? But the point is, just because something is favored, spontaneous, doesn't mean that it happens fast. It just means it will happen. Okay? Okay. So, ladies and gentlemen, the last section in this chapter is different from how I covered this last year. Here's another place where this year's AP curriculum has changed from last year. Okay? this is an equation that used to be on your equation sheet. It is not on this year's. Does that mean you need to memorize it? No, because you will not be doing calculations with it, okay? The calculations are not on the AP exam. Now, you will need to understand it conceptually, but you're not going to be doing any calculations. But I do want to explain to you sort of the situation in which you would use it. Okay? So just to recap, guys, just to review, you said delta G is what you use to decide whether a reaction is favored or not. Good. There's two of them. What makes them different? Okay, what does that degree symbol mean? At standard state. Do you remember what that means? Standard state conditions? Yeah. Okay, 25 degrees Celsius. What's the pressure of any gas? 1 atmosphere. What's the molarity of any solution? 1 molar. Okay, great. Well, let's say that you're doing a reaction where, let's say you have all gases, and 2 of your gases are at 1 atm, but a third gas is at 8 atm. If even one part of your system is at non-standard conditions, then your whole system is not at standard state conditions. Does that mean you can't predict whether it will be favorable or not? No, you can. You would just have to calculate delta G non-standard to figure that out. But then the rules are the same. If it's negative, it's favored, positive, no. Okay. Now, what is R? Okay, the gas constant. What's T? Temperature. Q is something we have seen before. It's called a reaction quotient. And if you don't remember that, I think you'll remember this. Okay, Q is calculated exactly the same way as K, the equilibrium constant. Products divided by reactants. Do any of you remember what makes Q different from K? Thank you. Okay. Q includes molarities or pressures, products over reactants, that are not at equilibrium. Okay. But again, you're not going to do any calculations with this, so what will you be asked to do? Well, let me show you. Okay, we're going to do this question together, all together. We've got a balanced equation, and then it says indicate whether delta G, please notice there is no degree symbol next to it, non-standard conditions. Indicate whether delta G increases, decreases, or does not change when the following changes are made to the reaction above, and the little hint is to think about Le Chatelier's principle. Okay, well, first of all, when we make these changes to this reaction, we are going to push it out of equilibrium, first of all, but I'm also making a change that's causing the conditions to no longer be standard state. That's why that degree symbol is not there. For example, okay, let's look at number 1. It says carbon monoxide gas is added. All right? If I add more of this gas, that means its pressure is no longer 1 atmosphere. I'm no longer under standard state conditions. Now, tell me this. Think back to chapter 5 or 13, or whichever one it was. I don't remember. If you add a reactant, which way will this shift? Okay, it'll shift to the right. You're absolutely correct. Well, Guys, anytime we have said thus far in this chapter, a reaction is favored, okay? Anytime we have said that, what we're really saying is that the reaction is favored in the forward direction, in the way it is written from left to right, reactants to products, okay? Let me just say that again in case you missed it. Anytime we have said so far, yes, this is a favorable reaction, what we're really saying is that the reaction is favorable in the forward direction. Well, look at what number 1 did. It caused it a shift to occur in the forward direction. So, let's say that this was already a favorable reaction. I've now made a change that's made it even more favorable. So if something is becoming even more spontaneous, even more favorable, would delta G be becoming more negative, more positive, or staying the same? More negative. Because what do negative delta G's mean? They mean becoming favorable. So I'm going to say that delta G decreases. This change, because it caused a shift in the forward direction, has made this reaction even more favorable. Question?
So you get in terms of the equation in the previous slide, like if CO is added, then Q becomes smaller, and you're subtracting smaller.
Exactly. Exactly. Yep. Okay, let's look at number 2. Hydrogen gas is removed. Which way will this shift? To the left. This change is causing the equation to move in the direction that is not favored. So what's happening to delta G? Okay. This reaction is becoming less favorable from left to right. This is a situation where this delta G is becoming more positive. See if you remember this next one. If you change the pressure, you increase it, how do you know which way the reaction shifts? Do you remember? Yep, Melanie. Goes to the side with fewer moles of gas. How many moles of gas are on the left? 3. And on the right? 0. So which way is this shifting? So what would you say for delta G? Decreasing. Becoming more favorable. Okay. Number 4 says temperature is increased. Well, remember, when we first talked about Le Chatelier, I said you can't answer a temperature question unless I tell you whether the reaction is endo or exothermic. Well, here I'm giving you that information. What am I telling you here? Okay, it's exo, which means heat is a what? Product. Let's write it in. Now let's come back here. Temperature is increased. Does that sound like I'm adding heat or removing heat? Okay, so I'm going to add some more product. Which way will this shift? Okay. So what do you want to say for delta G? Increasing. One more. This time I'm adding a product. What do you think? Why? Aha! You didn't fall for my trick. It's a liquid. Liquids don't affect equilibrium. What else doesn't affect equilibrium?
Solids.
Very good. So what are you going to say here? Remains the same. No change. No shift. Okay? Alright. So, again, folks, you're not going to be asked to calculate anything with delta G non-standard, but you will be asked to make predictions like this. Okay? Alright. Now, for those of you, I hope all of you, who went back and looked at the 2 slides that I didn't get a chance to cover last class, I briefly mentioned this statement, okay? Please notice that there is no degree symbol there. Delta G non-standard equals 0 if we're at equilibrium. Okay, now again, I know we're not using this equation, but for you mathy types, this will help you understand where we get an equation that is on your equation sheet. This is 0. And this all stays the same. But I'm at equilibrium. This is not Q anymore. It's K. I can rearrange this equation to be a little bit simpler and look like that, which is on your equation sheet. Okay, and let's just look at it again. Look at all the equations that you are given, that you don't have to memorize. You, in fact, now have 3 ways to calculate delta G standard, and they're right all together. They're boom, boom, boom. Okay. How do you know which one to use? It depends on the information that you are given. Okay. Now, to do a little bit of practice with this, we're going to do a problem out of the problem set together. Before I tell you which one, though, this is a natural log. All right, I do not want you all to get concerned about, you know, are we going to be discussing logs and natural logs in detail? Are we going to be graphing them and log functions and inverse log? No. Okay. In AP Chem, the extent of how much do you need to know about logs and natural logs is essentially, can you push the button on your calculator? Okay, so if you are a little fuzzy on that, don't fret. I will help you. Okay, but if you would, in your book, go to page 786. 786. I want you to do number 61, which is one of your problem set problems. Okay? 61. 61 actually asks you 2 separate calculations. I only want you to do the first one. Try this one. Now, I hear some discussion out there Does it matter which value for R you plug in? Yes, it does. Remember, guys, the values for R are given to you. And I want you to look at them, and more specifically, look at the units that go with them. Which one do you think is the right one to use?
Joules.
Okay, so, which number is that?
8.314.
8.314, because it's the only one that has joules in it. Now guys, some of you may be more familiar than others, more comfortable solving for an unknown that's tied up in a natural log. Some of you may be very uncomfortable with that. For you mathy types who are comfortable, how do you solve for something tied up in a natural log? Tell us.
Natural log is just log e to whatever, right?
Okay?
So wouldn't k equal e to the power of 2.908?
Exactly right. Ladies and gentlemen, in your calculator, if you push second and then the little button that says ln, go ahead and push it. Do you see a lowercase e? Do you?
Yes.
Okay. E to the power of whatever's on the other side will equal k. And let's see what that comes out to be. 8 something. 8.8. And remember, you don't need units for an equilibrium constant.
So then what you plug, when you plug that in, so then is the answer. So
Okay.
I can find that.
So, guys, to wrap this chapter up, tell me one more time, for the billionth time, if delta G is negative, what does that mean?
Favored.
Okay, the reaction is thermodynamically favored in what direction? Forward. Okay? Alright, great. Well, let's assume we're at equilibrium. And ladies and gentlemen, any equilibrium constant is always what divided by what? Products divided by reactants. Well, if this is my situation, and you're saying that the forward direction is favored, am I making a lot of product or a little product? A lot. Big product over little tiny reactants. A lot of products, not that many reactants. So folks, what does that mean about the value for K? It's big. Or let's be more specific, greater than 1. Okay? Alright. What does it mean, again, for the billionth time, if delta G is a positive number? Okay, the reaction is not thermodynamically favored in the forward direction. So when would it be favored? In the reverse direction. So, do I have a lot of product or a little? A little. What does that mean for this number? It's small. It's a fraction. It's less than 1. Okay? It's never negative. K's can't be negative, but it will be less than 1, a fraction. Okay? And if you think about this equation that we just used a moment ago, if this is equal to 0, For those of you that are comfortable with your logs and natural logs, that means k must be equal to 1. And what's the natural log of 1? 0. Which means it doesn't matter what these two numbers are. Your answer is going to be 0. So, ladies and gentlemen, the only purpose of this chart is the fact that knowing the value of delta G at equilibrium can tell you, give you an indication of the quantity, the value of K. It can give you an indication as to whether it's going to be a big number, a small number, equal to 1, what. And that is it for this chapter.